My name is Victoria Valenzuela. I'll be doing gas detection using portable deep UV absorption spectrophotometry. It's by Suleiman Khan, David Newport, and Stephanie LeCalve. So gas detection is an important part of industrial and domestic life because it's all around us and there can be toxic and flammable gases. Gas detection is important because we can monitor greenhouse gases for environmental problems and for diagnostics of diseases within the body. So methods used were UV spectrophotometry, and it was applied to different gases. It provides a highly sensitive, reliable, and selective approach for gas sensing. So OGCs were used, and it's a platform where photons, UV radiation, and gas analyte molecules interact. So there's a trade-off between sensitivity and portability of the spectrophotometer for specific gases. There's two types of OGCs: single-pass gas cells, which are longer optical paths with low volume, and there's multiple pass gas cells, which require a higher volume and have limited time resolution. Aluminum-based HCWs, hollow core waveguides, are light tubes for transmission of high peak power laser lights. So they were used. UV sources are characterized using wavelength range, optical output stability, lifetime, and input power. Photodetectors, UV photodetectors, features high sensitivity, excellent photocurrents, incident optical power, and high spectral sensitivity. So these gases were applied to UV absorption spectrophotometry, ozone, which is in the stratosphere and troposphere, nitrogen dioxide and sulfur dioxide, which are both highly toxic in some way to the human body, so it's important to detect these. Another one was BTEX, which is benzene, toluene, xylene, and ethylbenzene. So here is the experimental setup with aluminum-based HCWs. Then we have the experimental setup with lamps and photodiodes, which are the photodetectors, and UV lights. Then we have the setup with BTEX of the actual spectrometer. Here is the gas inlet and the gas outlet, and here's where it detects and senses the gas. Then, so for the photodetectors, photoconductors are at a disadvantage because there's large dark current, but they're simple design and easy process control and high gain. But UV detectors have low dark currents and quick time response and high sensitivity. The only thing is there's higher absorption losses. So for the UV sources, there's LED, deuterium lamp, and mercury lamp, which mercury lamp is only really important for because it matches strongly with BTX, but other than that, it has low output stability. Deuterium lamp is more stable than all of them, but there's a high intensity light output. LED has portable, low cost, low power consumption. So the results are that BTEX with deep UV LED has a fast response time, but the carrier gas is N2, and that's with the photodiode. Ozone with LED and the photodiode didn't produce a result for the time response, and nitrogen and sulfur dioxide with LED and photodiode produced 10 meters per second, but with the carrier gas of N2, so it's similar to that of BTEX. So in conclusion, several molecules in environmental and domestic significance would show strong UV absorption. LED offers a stable, efficient, portable, and a narrow emission band. UV is a source for analytical applications with ease of alignment, and it's low cost with an enhanced lifetime. The only challenges is that LEDs are the need for a highly stable power supply source, so they have lower power emission. Since the aluminum-based HCW gas cells were primarily used, it's more efficient for UV transmission, and HCW provides the most potential to be used as a gas cell because it did have a longer optical path with a smaller footprint area. UV detectors would be high spectral sensitivity with visible rejection and minimal dark current and resistance against UV aging, which would go hand in hand with the LED because it had an enhanced lifetime. So overall, for UV spectrophotometry for gas detection, you'd want LED with aluminum-based HCWs and photodiodes. And here are my references.